Today I'll be doing the first and only practice problem for homework number 9. Okay, we will start by restating the problem, which I will do in the form of a picture. So we have a pane of glass, which is separating a room. I'll draw a little chair here. There's a room from the outside. Okay, now inside this room we have air, and that air is at a temperature of 15 degrees Celsius. Now this is a winter day, and so the outside is cold. It doesn't tell us what temperature, but what we know is that the temperature of the surface of this glass window is at 0 degrees Celsius. We're also told what the emissivity of our glass is, which is 0.94. Okay, we're also told that the surroundings, so all of the surfaces inside of our room, are at 15 degrees Celsius. We're also given a utility rate, so how much it costs you for electricity, assuming you have an electric heater. And that's 8 cents or $0.08 per kilowatt hour. Okay, so that's our utility rate. We're given the temperature of the window, the temperature of the air and surroundings inside. And then we are asked to find two things. A, why is there frost? I think we'll switch colors. Why is there frost on the bottom? Maybe we'll go for white. Okay, so why is there frost on the bottom of the window? And then B, what is the rate of heat loss from the window, from the room into the window? So this is 15 degrees C, this is 0, this is something less than 0. Heat is transferring out. What is that Q loss? And what is the cost per day of having your window there? In other words, how much is it going to cost you every day to be losing heat from this window, maintaining your inside at 15 degrees C? Okay, let's talk briefly about our approach. Our approach is we're going to do an energy balance on the window. And as we do that energy balance, we're going to find that we need to solve for some sort of H bar, right? We need to find the convective loss from the room into the window, and that's going to require H. And in order to do that, we're going to need to find the Nussel number. Okay, so that's kind of the approach we're going to take here. The last general problem setup we're going to do is our energy balance control volume step, which I will do up here. Again, we're measuring the heat loss from the room into the window. So we're going to draw our control volume around our window, and we have two things coming in, Q convection and radiative transfer from the room into the wall. So we're going to use those two things in order to find the total heat loss. So as our problem approach, we're going to say the total loss, the total heat loss from our room into this window and then eventually outside is just equal to both of these terms. So the loss from the room into the window by convection and by radiation. Okay, well, we can write each of these as convection is the average heat transfer coefficient for the entire window times the surface area of the window times, and then the way we're going to write this is T infinity minus Ts, because heat is transferring not from the window into the room, but from the room into the window. Also, we're going to write Q rad, which is using what we kind of call the Stefan-Boltzmann Law, our emissivity of our window, which also would be the absorptivity of the window, multiplied by our Stefan-Boltzmann constant, times the temperature of the surrounding, the hot thing, subtracted from where the heat is going, the cold thing, Ts to the fourth. Okay, so we're just going to put both of these into our final equation, but there's a problem, right? We need to know what h bar is. And so in order to do that, we're going to have to find the Nusselt number. Okay, but before we do any of that, let's find our properties from Appendix A. Okay, so for air, we're going to evaluate our properties at T film, which would be temperature of the surface plus T infinity divided by 2. So the average temperature of the fluid. All right, when we do that, then we can solve for several different properties, including the kinematic viscosity, 1.411 times 10 to the negative 6th meters squared per second. We can also find the thermal conductivity of the air, 0.0247 watts per meter Kelvin. We can also find our thermal diffusivity, 1.986 times 10 to the negative 5th meters squared per second. And finally, the Prandtl number, 0.71. Okay, we've got our properties. We've got our approach, but I actually forgot to come back to part A. Why is there frost on the bottom of the window? So let's start with part A, and we'll do that by drawing our window. So here's our window, which kind of goes off this way and this way. Okay, so remember, this window is cold, and the air is hot relative to each other. We have hot air, or 15 degrees C, and then the window is cold at 0 degrees C. What that means is that the air molecules directly touching the window are going to adopt the temperature of the window, or 0 degrees Celsius. Now, let's look at molecules approaching the bulk temperature of the air, 15 degrees C, right? So as we go out, this one is at 0, this one's at 15 degrees C. And we know that based on the ideal gas law, as we showed in class, as the temperature goes down, then the density goes up, right? As this goes down, density goes up. Well, the temperature of the fluid by the window is colder than the temperature of the fluid outside of the window or closer into the room, which means our density near the window will be higher. Because it's more dense, it weighs more, it's heavier, and it's going to sink. So these molecules are going to sink. But we still have the no-slip condition. So the air molecules directly touching the window will not sink. The air molecules directly far away from the window won't sink, and we'll have some sort of temperature profile that looks like this, going downwards. What that means is we are going to develop a boundary layer, just like we did with external flow. So we have this boundary layer just like we did for forced external flow, but now for free convection external flow. And just like before, this thickness of our boundary layer grows as we go down. Because the thickness gets larger, then the distance of heat transfer also gets larger. And that means that it's harder for a given delta T to transfer an equivalent amount of heat. So our convection heat transfer value H is going to go down as we go down the window because our boundary layer is growing thicker, making heat transfer harder. So because H is going down, but Ts and T infinity are set, our heat rate is going to go down. And by the bottom of the window, it will drop such that we actually have frost on the bottom of the window. Okay, so now that brings us to part B, which is we need to find what is our Q loss and how much is it going to cost us per day. Okay, Well, we've already established what Q loss is. We said we need to find H bar, so we need a correlation. So what correlation are we going to use? Well, we have a vertical flat plate. And we don't know yet if it's laminar or turbulent. But we actually aren't going to have to know for this correlation, turns out. Because all we need to know is vertical flat plate. We go to our book and we find equation 9.26, the Churchill-Chu correlation. This one works for any Rayleigh number. That's pretty cool, right? So for any Rayleigh number, we can use the Churchill and Chu correlation, which, despite my better judgment, I'm going to write on the board so that we can have this problem complete here in this video. So it's 0.825 plus 0.387 times the Rayleigh number to the 1/6 divided by 1 plus 0.492 divided by the Prandtl number raised to the 9/16, and that whole thing, sorry, that's not right. That whole thing right there is raised to the 8/27, and the entire quantity is squared. Wow. Okay, so that is our correlation. And remember, we're going to use our correlation to solve for H, because the Nusselt number is also equal to H times L times K of the fluid, where L is the height of our window, which actually was given to us. I forgot to restate that. It is 1.8 meters, and the width of our window is 1 meter. Okay, so if we can find the Rayleigh number, plug it into this correlation, set it equal to HL over KF, we can find H. So now we just need to find the Rayleigh number. So the Rayleigh number is the gravitational constant times beta, where beta is our coefficient, our volumetric expansion coefficient, times T infinity minus Ts, our temperature difference, all times our length cubed divided by our kinematic viscosity and thermal diffusivity. Okay, we plug all of these in, remembering that beta is just equal to 1 over T, in this case T film. And when you plug all of these in, then you get that the Rayleigh number is 1.084 times 10 to the 10th. Okay, again, it doesn't matter if it's laminar or turbulent because our Churchill-Chu correlation doesn't matter. It has no restriction on the Rayleigh number, which is pretty cool. So when we plug in all of our numbers, we get an average Nusselt number of 258.9, which we can use, like I said, over here to solve for H. So H is 3.6 watts per meter squared Kelvin. Okay, so now that we have H, we can plug it into this part of our equation, solve for this, and add them together to find what Q loss is. And when you do that, you get that Q loss is 223 watts. All right, the final part of our problem is to find how much this is going to cost us per day. Okay, so this is watts, right, or joules per second, amount of energy per second. All right, so we're going to write that out, 223 watts. Now, our utility rate is given in cents per kilowatt hour, where a kilowatt hour is actually a unit of energy, representing 1 watt that occurs for an hour. So it's 1 watt of power over 1 hour of time. So what we're going to do is convert this into kilowatts by saying, well, that's 223 watts. There are 1,000 watts in 1 kilowatt. Then we're going to multiply, so our heat rate in kilowatts multiplied by our rate, where our rate is how much money it costs us, $0.08 per kilowatt hour. And then finally, this would be on an hour basis, right? Because that's kilowatts per hour. So we need to multiply by 24 hours in a day. So when you multiply all of these things together, then you get the total cost that your window will cost you, and you get $96 per day. Sorry, $0.96 per day, or 96 cents per day. That's how much it's costing you to maintain this window with your insides at 15 degrees C and the window at 0 degrees C. Okay, that's our problem. Thanks for watching.